Okay. Hello everybody. My name is Ibrahim Abu Kharmeh. I work for Huawei, and today I'm gonna speak to you all about code size analysis and ZC extension. It's really important to get into to understand why code size is important. Just to get into speed why we're doing this. Code size. So consumer products are very cost sensitive. If we improve the code size, then we reduce the requirements for ROM and flash and ROM, and we also potentially can improve the performance because we will have better cache hit and buffer utilization, and that also can potentially give us power saving benefits. RISC-V has already an extension for compressed instruction, which defines 16-bit encodings for most common instructions. The code size density is sometimes worse than competitor cores in embedded space. This is not only due to the ISA, but also toolchain and compiler support. This work was done for code size TG, and our goal is to get the RISC-V code density superior to other ISAs. And this can be done in two stages or in two steps. First, we need to figure out issues and report them in toolchain and compiler and try to get them fixed. And the other step is to try to find an ISA extension that we can aid the C extension for code size density. So how can we achieve this? How can we achieve this better code size density? Well, first we need to be able to measure things and try to figure out why things the way they are. If you can't measure it, you cannot improve it. So what we need to do is that we need to analyze existing RISC-V codes and figure out, search for optimization opportunities. And then after that, we need to find possible optimizations, either be it new instructions or either be it optimization for toolchain and compiler support. And after that, after we find these possible optimizations, we need to make sure that these optimizations or new instructions apply to a varied different loads. So we need to make sure that they don't apply to a specific load, but rather apply to a wide range of loads that various programs that RISC-V aim to support from. And then we need to make sure that these instructions or enhancement don't have a high penalty for performance, or if they are instructions, then the implementation complexity is not significant performance hit. Okay, so and this loop of searching for optimizations and checking that they are valid, it needs to be really short. So when we are the time we need to check, we need to be able to quickly check if these are valid instructions, because when we are tuning instructions, it's really unreasonable to actually go and change the compiler and compile it and then try to compile a varied benchmark for every time we need to check to tune these instructions or enhancements. So we need to find a way to actually figure that out without actually doing changing the compiler. So I wrote very simple Python script to try to help us analyze various the ZCE extension that code size TG is working on. With various instructions. So the script is really simple. It just takes an executable elf file, pre-compiled executable elf file, and it just calls objdump on it. And it obtains the disassembly and symbol tables. And then it parses the objdump output. And then it constructs an instruction record, which is really a parse disassembly and various flags to indicate where control of flow changes. So after that, we can use this parsed structure to figure out possible enhancement, either be it toolchain enhancement or be it new instructions. And then we can use the same structure to overwrite it and figure out the gains from these enhancements or new instructions. So to figure out new optimizations or instructions, we can either do that manually by just looking at an executable and figuring out what things are taking most space and try to optimize them, or we can try to abstract from that and try to make that like figured out by the script. So for example, we can track how instructions of destination registers or destination operands get used in different other instructions and use that chain to figure out a fused instruction that's very common and can be used or proposed. Or we can track also the other way around, how sources are generated and try to combine them. When we're tracking instructions, I would face the issue with the control flow instructions. Now, if we reached unconditional call to outside the current function, we would only save the tracking buffer if we're tracking a caller saved register. Otherwise, we'll just discard the tracking buffer. For conditional calls or branch targets, we'll just stop and discard the tracking buffer because we don't know which direction the branch will go. And if we don't know, then we wouldn't be able to tell for sure if we confuse that instruction or not. So to verify these optimization that we propose, we first thing first. So most of the current ZTE instructions either convert a single normal 32-bit instruction into compressed 16-bit one, or use a common instruction sequence, like I said earlier. So to verify them, what we can do is that we can construct the instruction record, like I showed earlier, and then we can find either the 32-bit instruction or the sequences, and replace them with the proposed instruction. And then we can just use the same instruction record to calculate the record size, the total record size. We can apply optimization additively to the instruction record because it's just the normal structure. We can, for example, if we have an overlapping optimizations, then what we can do is that we can apply the first one and then apply the second one, and then we can see how the extent of the overlap between these two instructions or these different proposals. Okay, for example, malai and mul and c.mul, we propose the instruction compressed multiplication, which was not available in original compressed extension, and this would have some certain overlap with another proposal, which is multiply a register with an immediate value. So by applying these additively, we'll be able to tell the overlap. And likewise for table JAL, which is another instruction I'm going to speak about shortly, and existing msave restore, which is a milli-code optimization, and also pushbob, which is another optimization I'm going to speak about. So a short overview of ZTE extension. ZTE extension have these instructions, and it's the main aim for it is to aid C extension to improving RISC-V code size. So first thing, it makes sense if somebody would want to reduce the code size for RISC-V. First thing, they should use C extension, obviously, and then they should look at ZTE. And it includes these instructions, and they are in two different sets, two subsets. Some of it reuses some encoding space from the extension, but some of it don't. That's why they are split here. And the main two instructions, the biggest things that save code size are two instructions. One of them is called table JAL, and one of them is called pushbob. The extension is being at the moment, the toolchain and simulator support is being developed by CAS, and LLVM, GCC, SPAC, and QEMU already developing pretty rapidly. So let's see how we can apply the flow that I showed earlier to analyze instructions on one of the example instructions, table JAL. So for table JAL, its purpose, this instruction is to give like, for example, often we see that instructions when we have jumps, it would either a lot of times they would not fit with the short range of C.compress instructions of jumps. So it would force the compiler to use 32-bit instruction or 64-bit sequence, so AUIPC plus JAL. This can waste a lot of code size. So this stable JAL would have a table in the memory, and it would jump, and then we would have a new instruction that would jump to various entries in the table. And the linked register would depend on the actual instruction. So we split this table into three different regions, and each region would link to a different register. And location of this memory is configured by CSR. So to actually analyze this, what we can do is that we can get all the function calls in a certain program, and then we can eliminate all the ones that won't gain any from savings. And then we can change the weights of each call to make sure that the one get more savings get counted as a higher priority. And then we can get the most common ones. And then what we can do is that we can replace the entries of JAL and JAL-R likewise in the instruction record that I showed earlier. And then we can calculate the total new instruction record. This is, and then we can reference the new instruction record to the original instruction record size to calculate, to see how much we save. What we can do, we also have to compensate for the actual table size because we waste the size of the table size. So we need to make sure that we count for that. The other structure that I wanted to speak to you about today is push and pop rate. These instructions are used to save and restore multiple values to and from the stack, because very often in functions, ablog and prelogs, what we need to do is that we need to save and restore saved registers, like is shown in this example from the stack, and also return address. So every time this happens, that we waste a lot of code adjusting the stack and actually storing and saving. There is already a millicode to do this, but it can be sometimes not efficient. So there is a proposed instruction, proposed couple of instructions that do that. To analyze how much savings we get from this, we detect the positive and negative stack adjustment within a block. And then we find the corresponding load and store within that stack frame. And then if we find, oh, this instruction also do a couple of embedded moves, because after we often save the saved registers, we have to move stuff from argument registers into saved registers. So this instruction also includes these. So if we find any embedded moves here, we find them and we see if they fit the instruction encoding, and then we replace all of these instructions with a single instruction like shown here for push or pop rate, because pop rate is just the same as pop, which just loads registers, load back data, but it also returns directly. So what we spoke about earlier in the beginning is that we want a way to find optimization, and then we want a way to evaluate optimization and make sure that they actually apply to a wide set of range of applications and compilers. And we want to make sure that that we don't waste encoding space. So the third point, which is the encoding space, and we make sure that our instructions don't actually waste encoding space. What we can do is that we can tune the encoding space, and we can just run the fitting criteria for our optimization. Then we can run the replacement again and again until we see the sweet spot for the maximum code savings while wasting the least amount of encoding space, because really encoding space is really valuable. We can see here for multiply immediate, around 10 bits, we saturate the savings, and beyond that, it wouldn't make much sense to use these 2 bits unless we really have the encoding space. So when we are benchmarking for code size task group, we need to consider a lot of things. We need to consider the actual program that we are benchmarking, either be it a low, a very simple program like an IoT with a couple of sensors, IoT framework with a couple of sensors, or a machine learning or a signal processing or very heavy program, and the language that it was written in, and the compiler that it was used to compile, and the actual ABI. eABI is not freeze as far as I'm concerned, but we need to actually consider that. And if the program is 32-bit or 64-bit, and we also need to make sure of the side effects. And if we propose an instruction that costs us a lot of performance, penalty, or power, or implementation complexity, then it might not make sense to actually use that. So we want to also consider that. So to actually achieve all these goals, all these factors, to consider all these factors, we are using currently this suite of benchmarks. We obtained we are using the top 30 biggest 30 DBM packages recompiled for RISC-V 64 bits, and we're also using the V8 JavaScript engine for this V8 is generally written in C++, so that's a good use for C++ tests. And all of these are, so Opus and L3C are audio codec, and mbench, Kharmeh, and spec CPU are just a collection of benchmarks that used to evaluate general CPUs. And test float is floating point test, and Arcus and Zephyr and our own code are for Arcus applications. And we also compiled these in using Clang and GCC to see if different compilers, if our instructions are valuable and usable for both compilers. So from all of that, we can get the actual results of the savings. And I split the results into two sections. First is for table JAL, which is PushPop. And the second slide, I will show the rest of the results. You can see here that it's the savings is almost 15% or 20% for these instructions. The last column is PushPop with respect to MSR, because it doesn't really make sense to get the values of PushPop without comparing it to the existing software implementation, which is a millicode MSR routine, save restore routine, which can be like triggered from the compiler by msave restore flag. The last slide I want to show you before I conclude is the complete results for everything and for everything else. Well, there is much more results, but this is what I was able to fit in a single slide. And you can see here the various instructions that we are, the various other instructions that we are currently considering, and the results for each of them, and each benchmark and the contribution. Really, what I want to get away from this, show from this slide, is that first thing first, we can see that some generally complete savings for only these instructions is significant. What's worth mentioning here is that a significant amount of these benchmarks are mbench benchmarks, which don't actually have a significant amount of code size, so some optimization don't apply to it. The other thing is that we can see similarity between the GCC compilation and Clang compilation, which is really a relieving thing. It's very nice to see actual similarity. Like we can see things that are gaining from GCC, which we did the initial evaluation on. They are still gaining from EDF, from Clang, but they are even gaining more from Clang. I was looking at this shortly, and I think one reason is that it appears that Clang generally prefer to use the 8 compressed registers that are in the compressed format. And the other thing I want to mention here is that sometimes the compiler used variable signedness differently. So the two of these instructions that so the signed load and unsigned load, sometimes the values of the savings are swapped between two different compilers, but the complete value is almost very similar. So what we did when in code size CG and the work we did to analyze to benchmark various instructions is that we analyzed the instructions we are proposing, and we made sure that they are applicable to a wide range of applications and commonly used compilers. We have way more results than I showed here, and you can access them from our official RISC-V code size optimization task group, our official repository here on this link. And we tuned the ZCE instructions that we are proposing for more maximum code size savings while using the least amount of encoding space. And we are identifying issues and possible enhancement in toolchains, and we are reporting them currently. And that's all from me. If you have any questions, please ask me here or on our official mailing list for RISC-V.
Hello. Well, thank you. Thank you. Yes, for questions, go ahead and put them in the Q&A. And if you, Ibrahim, if you can go over to the Q&A and check out, see what people are asking, that would be great.
Sure. Thank you very much.